Quantum mechanics is not a license for magic. It does not let you manifest a parking space with positive energy, and it does not care what you had for breakfast when an electron decides where to land. The quantum realm is stranger than any superstition we've invented about it, and far more interesting. Let's start with one of the most abused ideas. Consciousness collapses the wave function. In the early days of quantum theory, physicists like von Neumann and Wigner wondered whether a measurement required a conscious observer. Today, most working physicists think that's unnecessary. When we say a wave function collapses, we really mean a quantum system that could be in many possible states interacts with something in the environment. Air molecules, photons, a detector, and those possibilities get irreversibly recorded. This process, called decoherence, turns fragile quantum superpositions into the single definite outcomes we see. Your brain is just one more messy, warm, classical object in that chain, not a magical quantum referee. Then there's entanglement, often described, thanks to Einstein, as spooky action at a distance. It sounds like faster-than-light messaging. It isn't. When two particles are entangled, their properties are correlated in a way that can't be explained by any shared secret instructions assigned in advance. Bell's theorem and decades of experiments show this. But when you measure one particle, you don't send a usable signal to the other. You just reveal one piece of a joint pattern. Only when you compare notes, using normal, slower-than-light communication, does the non-classical correlation appear. The universe keeps locality for information, even while breaking our classical intuitions about independence. Another myth. Quantum mechanics says everything is possible, anything can happen. Not quite. The theory is wildly permissive compared to classical physics. Particles can tunnel through barriers, virtual particles flicker in and out of the vacuum, but every process comes with a probability, often astronomically tiny. You will not tunnel through your chair because the odds are so small that, on average, you'd have to wait far longer than the age of the universe. Quantum laws are rigid. They just assign reality a menu of options rather than a single script. So what are the real mysteries? One is the measurement problem itself. How exactly do we go from smooth, deterministic wave function evolution, governed by the Schrödinger equation, to the sudden random-looking click of a detector? Competing interpretations disagree. The many worlds view says the wave function never collapses. Instead, reality continually branches, and every outcome happens in a larger multiverse. Objective collapse theories say there really is a physical, stochastic collapse, perhaps triggered when enough mass or complexity is involved. Bohmian mechanics adds hidden variables and definite particle paths. All make the same predictions for almost all experiments we can do so far. Nature is keeping her cards close. At the frontier, the quantum realm is not just a playground for philosophy, it's an engineering project that may reshape civilization. Quantum computers, if scaled from dozens to millions of high-quality qubits, could simulate complex molecules, design catalysts for carbon-neutral fuels, and crack some cryptographic codes that currently secure the internet. Quantum sensors already push to the edge of what's allowed by the Heisenberg uncertainty principle, using entangled atoms and squeezed light to measure time, gravity, and magnetic fields with record precision. And in space, observatories like LIGO and Virgo detect gravitational waves using kilometer-scale interferometers that rely on exquisitely controlled quantum states of light. Pushing deeper into the quantum realm may even rewrite our picture of space-time itself. Some researchers suspect that entanglement is not just a weird feature of quantum fields living in space-time, but the scaffolding from which space-time emerges, a kind of cosmic information network that, when densely connected enough, feels like smooth geometry and gravity. To test such ideas, we'll need new experiments, new mathematics, and new ways of thinking that bridge the smallest scales with the structure of the cosmos. The deeper we go into the quantum realm, the less it looks like a hidden world beneath ours, and the more it looks like the operating system from which our familiar reality is compiled. So the next question is, what happens when that operating system itself starts to bend under the weight of gravity?